Hello, everyone. Welcome back to the final lecture of this thermodynamics module. Today, we are going to talk about the heat effects and chemical reaction equilibrium. Just a quick recap of our lecture 4. Lecture 4, we introduced the phase rule, using this phase rule to determine the number of intensive thermodynamic properties that we need to have to determine a state, right? That F is the degree of freedom, if you may. And then we went ahead to talk about the multi-component system or a mixture, right? For mixture, really, to quantify each individual species impact on the total properties, we introduce partial molar properties. And remember, partial molar property, a special example is that the chemical potential is the partial molar Gibbs free energy. And then from there, we actually use this equation to calculate the mixture properties, right? Again, in the ideal gas mixture state, ideal gas mixture model. So the mixture property is actually going to be able to calculate using molar fraction and also the pure species property in the ideal gas state as well. Remember, for enthalpy and internal energy, you don't have any additional terms, just like the molar fraction times their pure properties sum them up. But for entropy and Gibbs free energy and chemical potential, right, you actually need to have additional terms. And these additional terms is because of the difference in pressure, system pressure, and the partial pressure of these species. And analogously, we can also have an ideal solution model. So where you can see, right, pretty much like they mimic, but instead of yi, we use xi to represent the molar fraction of the species in the ideal solution, right? And then from there, we actually, for phase equilibrium to occur, we said, right, the chemical potential of each species in different phases will be equal, right? And specifically for vapor-liquid equilibrium of a real fluid, eventually you can get this correlation between the molar fraction in the gas pressure, system pressure, and then phi, and then gamma I is the activity coefficient, and then xi is the molar fraction of the species I in the liquid state, and then pi saturation is the saturation pressure. So basically at phase equilibrium, right, your xi, yi, phi, gamma I, pi saturation, total system has to follow this equation, right? Now, pi saturation, you can calculate using Antoine equation. So as long as you know T, you can calculate pi saturation. Gamma I, we give you a few different type of equation to calculate. Again, it's going to be a function of T and molar fraction. And then capital Phi is going to be a function of temperature, pressure, Y. For ideal solution, this is for real fluid, right? We derive this equation using fugacity concept. And then for real ideal solution and ideal vapor, mainly at low pressure, the gamma I goes to 1, capital Phi goes to 1. So it eventually this general equation reduced to Raoult's law for ideal solution models, ideal gas mixture models. Okay. All right. In today's lecture, we are going to talk about the heat effects and chemical reaction equilibrium, right? By the end of this lecture, you should be able to apply thermodynamics to chemical mixing and also chemical reactions. We are going to first introduce you heat of mixing and heat of reaction, and then consider this Gibbs free energy of a reaction, right? And then how this Gibbs free energy is related to the equilibrium constant. And from the equilibrium constant, how can we calculate the equilibrium compositions after a reaction reach equilibrium? And then we will talk about the temperature pressure dependence of this reaction equilibrium. Okay. All right. First, heat of mixing. Heat of mixing here, we are really talking about a physical mixing process, right? We are not talking about a reaction yet. Okay. So in this particular case, let's consider a chemical mixing process. Let's say to start, we have a solution at XA. Let's say your solution contains water, and then you contain like a specific salt, and then this solution contains XA molar fraction of salt in this solution, okay? And then MA is the mass of the solution of this solution particularly. Let's say the solution is at temperature TA, okay? And then you do you are trying to mix this solution with another solution, same thing, right? Sodium salt liquid water solution, but now you have a different molar fraction. Let's say the salt molar fraction is at XB, okay? And then MB is basically the mass of this particular solution. And then let's say the temperature of this solution is TB, okay? So these solutions are binary mixture, right? You contain liquid water and salt. And then you have different mass here. And then you mix everything together. It will still be a binary mixture because you only contain water and salt. But the molar fraction will change, right? So your molar fraction XF, well, depends on MA and B, XA, XB. So you just like simply do a mass balance to figure out XF, right? Assuming MF is equal to MA plus MB because you don't have mass loss due to physical mixing, okay? All right. And then now we want to, right, so mass balance, you can figure out XF. But how do you figure out the TF, right? TF really depends on the heat of mixing, right? So we want to first calculate the heat of mixing, right? So basically, if it's a exothermal heating process, then you are giving out of heat, right? So the heat is going to be, negative. But if you are absorbing heat during the mixing process, you are actually, your Q is actually positive, okay? So, but first, let's talk about the heat of mixing, how you can actually calculate that, okay? So now before we talk about heat of mixing, we need to first define like enthalpy, right? Enthalpy, let's say for this particular solution at this particular molar fraction per unit mass, you have a specific enthalpy, okay? Or per mole of this solution, you have a specific enthalpy. So you have HA, and then HB, and then HF, right? Now these H will only depends on the molar fraction, okay? It does because these are already normalized to their quantity, okay? And then usually for different material, different solution combination, right? You actually have enthalpy as a function of molar fraction plot. For example, sulfuric acid and water, you can actually look the H values at different compositions. If you are interested, you can read the additional slides in this lecture, okay? All right, so in general, right, the change of enthalpy after mixing is going to be just equal to delta H mix, right? The final H value minus initial H value add together. So final enthalpy is going to be the mass of the enthalpy times the specific enthalpy of the final solution. Minus initial is going to be MA times HA plus MB times HB, okay? So this is the change of enthalpy after mixing. Now, how does this correlate to heat of mixing, right? So now usually, remember, usually heat mixing under constant pressure. So usually when you do this mixing experiment, for example, we're usually just like mixing them in open air, right? Now, if you think about your solution is a system and then your open air is the surrounding, so atmosphere pressure, so the pressure of your system is always constant, right? So if it's a constant pressure process, in lecture 2, we already said, right? If it's constant pressure mixing, then dH is just equal to dQ. Okay, so dH is the change in enthalpy, and then dQ is basically the heat, right? The heat involved during the mixing, or basically we say dQ is just heat of mixing. And then change of enthalpy is equal to the heat of mixing under constant pressure mixing process, okay? And then these are the two common under constant pressure, right? We can also maintain. We have two common mixing processes. One is called isothermal mixing. So basically, when you do the mixing process, right, you don't want like the solution to overheat or less heat, right? You sometimes like you just maintain the temperature of all the solution constant, right? So TA equal to TB equal to TF, okay? So if it's exothermal mixing process, right, you generate heat, the system may rise in temperature, but basically you need to just like adding some cooling medium so that to absorb the heat that generated and then maintain the temperature constant. Okay, that's a pretty common practice in chemical engineering processes and also in lab operations when you operate a mixing process. Okay, so like I said, exothermic, your Q is going to be negative, and endothermic is going to be your Q is going to be greater than 0 or positive. Okay. And then you can also perform mixing in an insulated mixer, right? So in that case, you are talking about adiabatic mixing, and your Q is equal to 0, right? And then if your Q is equal to 0, then basically depending on your mixing species, your temperature may fluctuate, right? So this is like two common mixing processes. Okay. All right, so that's mixing or heato mixing, right? And then now we jump onto, I mean, in the additional slide, you have like example problem to calculate the heato mixing. So I will not go over details now, okay? All right, so now let's jump onto heato reactions, right? So now we are really talking about like, you have monomer A, monomer B, or reactant A, reactant B, reacting together to form a new product L and a new product M, right? You are changing actually the species into new species, right? So involving chemical reactions, okay? So here, let's say, usually when you write out a general chemical reaction, you have like, some A, B. AB is your reactants, LM is your products. And then you have like some stoichiometry coefficient in front, A, B, L, M. Okay, so let's say here, for example, CO2 in the gas state. Remember, you need to specify which state the reactant or the product is in so that you can look up like the correct heat of reaction, heat of formation for these materials. So that's you need to pay attention to this states, okay? So for example, in this reaction, 1 mole of CO2 will react with 1 mole of H2 and then forming 1 mole of CO and then 1 mole of H2O, okay? So here, the stoichiometry coefficient is basically just equal 1, 1, 1, 1, right? So, and then that's like your A, B, L, M values, okay? Now, when we talked about the heat of reaction, right? In the front, we have a word standard, right? We first need to talk about standard heat of reaction. By standard, what do we mean by standard, right? So basically, by standard heat of reaction, we are basically performing this reaction, okay, at steady state, at standard state. Now, by standard state, what we are referring to is that if this reaction involves gases in the reaction, right? By standard state, we mean these gases are at behaving like ideal gases throughout the reaction. And then usually the standard state is picking at a pressure of 1 bar or 1 atm. So these are the standard state for the gaseous species involving in the reaction, okay? Now, if we are talking about liquids or solids, then we are really talking about the standard state being the real pure liquids or solids, again, at 1 bar or 1 atm. So standard pressure. These are standard pressure. And then meaning that these usually behave like ideal gas or ideal solution. Okay. All right, so now if we perform this reaction as standard state, then you can actually calculate the standard heat of reaction. So standard heat of reaction, because we are operating this reaction at under constant pressure. So you already know under constant for a constant pressure process, delta H, right? Delta H is the change in enthalpy, okay? And it's going to be equal to the heat change, right? Heat exchange, right? So delta H is equal to Q. But now we want to point out for this delta H, you have subscript 298. So this subscript is used to refer to the temperature of your reaction operating at, okay? So here we are talking about room temperature 298 K, and then for standard state, we only specify the standard pressure, right? For temperature, you can vary. You can vary from room temperature or 0 degrees C, whichever you want. But as long as you specify the temperature, that should be fine. Okay. And then on the superscript, we have like a 0, right, on top. And this 0 just means these are standard state, like basically standard pressure. Okay. All right, so the standard heat of reaction is just equal to standard enthalpy of reaction is just equal to the heat of reaction. So from now on, we will just use delta H to represent the heat of reaction, okay? All right, so for example, for this particular reaction, the heat of reaction, right? So basically people operate the reaction the determination of this is through the heat of formation, which we will calculate, which we will introduce on the next slide. But just for now, let's say for this particular reaction, the heat of reaction is positive around 42 kilojoule. Okay, so this is like basically it's an endothermic reaction because it's a absorbing heat from the surrounding, right? And then this heat of reaction will depend on the chosen stoichiometry coefficients, right? Now, if you have like, instead of writing this reaction as 1, 1, 1, 1, you can also write it as 2, 2, 2, 2. Then for that heat of reaction, you need to double that heat of reaction, okay? All right, so now we previously mentioned, right, for this heat of reaction or standard heats of reaction, how do people measure it? And then people actually measure it by combustion reaction, but theoretically they can actually calculate from formation reaction, the heat of reaction. So now, first, let's introduce like formation reaction. So formation reaction is a reaction which forms a single compound from its constituent elements or molecular gases. So basically, this is an example of a formation reaction. So your reactants is either elements, right? So carbon is an element. And then O2, oxygen gas is a molecular gas, right? So for these two reactants, if you see, right, it's not a compound. You only have like one atom, one type of atoms, right? Carbon here, oxygen here. But now if you go through a formation reaction, carbon react with O2, forming CO2. And then now this is a compound, right? The product is a compound because it has two elements, two types of atoms in the gas molecule, right? So here carbon and oxygen, so it's a compound. Okay. And this particular reaction, right? Basically, you are forming a compound through two either elements or molecular gases, right? This is the formation reaction, okay? And then same thing, standard state is going to be the same, right? The standard pressure is either 1 bar or 1 atm. So that's your standard state, okay? Now, standard heat of formation is basically just like the standard heat of reaction of this formation reaction, okay? And then basically standard heat of reaction or standard heat of formation is just like a special kind of heat of reaction, okay? It's just like the reaction really requires your reactants to be either elements or molecular gases. And the reason why we want those is because we can assign these enthalpies for these elements and then molecular gases to be zero, right? And then you can figure out the changing enthalpy and then get the standard heat of formation, okay? Now, based on 1 mole product, right, the standard heat of formation of CO2, you can actually look it up. It's actually just equal to negative 39, around 393 kilojoule, okay? So based on 1 mole of product, right, delta HF. So here, delta HF means this is a formation reaction. So we are talking about the standard heat of formation of this particular compound, right? And then standard state the same, okay? And then here is basically just equal to the enthalpy, delta H 2980. Like I said, right, if you specify or assign the enthalpy of your element and then molecular gases equal to 0, then your heat of reaction is basically equal to the enthalpy change and then the heat of reaction of this particular reaction, okay? So formation reaction is going to be equal to just like the heat of reaction because these heat of formation of carbon is 0, heat of formation of oxygen gas is 0, okay? So yeah, here quick comments, right? For pure elements or molecular gases, the heat of formation is just essentially 0, okay? And then the heat of formation at 298K, standard heat of reaction at 298K for different species. You can actually look them up in the appendix table. Okay, so now here is just like example. I mean, the table that we are compiling different hydrocarbon gases. Again, pay attention to the state, right? For gas and liquid, you will have like different, for example, for toluene, your gas state, you will have much higher heat of formation than the liquid state, right? And then this is heat of formation. This is different gas. This is like the state of the particular species. And later we will also talk about the Gibbs free energy of formation. We will come back to this later. But for now, you can look these up, look these heat of formation up in this table. Okay, people already measure these for you. Like I mentioned, how people measure these is by combustion reaction. Okay, if you are interested, you can read the additional slide in this lecture. Okay, all right. So just to recap, right now we know how to find heat of formation, right? And then from the heat of formation, right? Remember, formation reaction, you really require your reactant to be either elements or molecular gases. But for a general reaction, for example, the reaction that we showed at the beginning, it involves like both compounds, right? A is a compound, B is a compound as well, C is another compound, D is another compound, right? For that compound, right, then we actually need to, you cannot simply use heat of formation, right? But for a general reaction, you can actually calculate the standard heat of reaction from the heat of formation by incorporating those stoichiometry coefficients, okay? So for this general reaction, let's say, again, you have A moles of A reacting with B moles of B goes to C moles of C plus D moles of D. And then in this reaction, when we write this out, A, B, C, D are all positive values, okay? Then the standard heat of reaction, again, this is going meaning 1 bar and then 298 K, okay? And then the standard heat of reaction is basically going to be the heat of formation for D times D plus heat of formation of C times C, and then minus heat of formation of A times A minus heat of formation of B times B, right? All at standard state. So basically, you're just like going to subtract, right? How much heat of formation you have on the product side minus the total heat of formation on the reactant side. And then the difference in these heat of combined heat of reaction is going to be, right, your standard heat of reaction, okay? Pretty straightforward, right? Now, for when we write out a reaction, right, we always have like A, B, C, D as positive values. But for mathematical analysis in the next few slides, it will be easier to introduce like these stoichiometry coefficients, right? Stoichiometry coefficient VI. This VI value can be either positive or negative, more specifically positive for product, negative for reactant, because when the reactant is decreasing or disappearing to form product, right? So now, in order, once we define the stoichiometry coefficient, right, we can rewrite this general equation as, you know, absolute value of stoichiometry coefficient. Again, V1, if it's on the reactant side, it's going to be negative value. But for when we write out the reaction, we want to see just like, you know, positive throughout, right? And then same thing here, V3 is going to be positive, right? V4 is going to be positive because they are on the product side, okay? Yeah, we already talked about, right? Sino VI for products is positive, for reactant is negative. And then for the standard heat of reaction, delta H 298 0 is just equal to summation VI delta HI F 298 0, right? So I here means basically which species you are talking about, right? So this, you know, A1, A2, right? So this is like A1, A2 for specific species. And then this VI is the stoichiometry coefficient associated with that particular I, right? For A1 is V1, right? And then for A2 is V2. And then for V3, for A3 is V3. Now, because we already assigned signs for VI, for the product side, it's going to be positive. So everything here is going to be positive, and then everything here will be negative. So essentially this, we will have like the positive sign minus reactant side, right? So basically this is just like generalize this and then but in a more convenient way for follow-up analysis, right? So delta H 298 0 is just equal to summation stoichiometry coefficient times delta H IF 298 heat of formation of standard heat of formation for a particular species. Okay. All right, so that's standard heat of reaction. So hopefully you understand how to find the heat of formation for different species, and then you come back to this reaction, you figure out the stoichiometric coefficient, and then you plug into this equation to calculate the standard heat of reaction for a particular reaction, okay? All right, now we want to analyze chemical reaction equilibrium, right? So for a particular reaction, right, you charge, let's say this piston, right? Inside this piston, you charge your reactants into this reactor, okay? And then let's say your initial temperature is 25 degrees C, and then you charge your reactants, which contain methane and water, right? This particular reaction is called steam reforming reaction. So you actually enter as steam state, and then like CH4, uh, reaction. Okay, so methane. Okay, so you have methane and water. Okay, or water vapor. And then at 1 atm, right? Again, constant pressure reaction. Let's say initially you have 1 mole of methane, 1 mole of H2O. And then you go through some reaction, wait for a long time, let the reaction to reach equilibrium. So basically they stop reacting, okay? You have a balanced mixture or equilibrium mixture containing both reactants and also products. Now, if the conversion is 100%, then you will only have your products in this chamber. But usually for a particular reaction, you will have some kind of equilibrium, okay? So you may have a mixture of like, residue reactants and also products. And then let's say again, the system pressure is still 1 atm, right? You are performing this reaction at constant temperature and constant pressure, okay? Now we want to ask, right, how many moles of CH4, right, methane that you still have left inside the reactor after reaching equilibrium, or at any instant time of reaction time t, okay? All right, so first of all, before we analyze the equilibrium, we want to define reaction coordinate. Basically, reaction coordinate is a parameter that characterizes the extent to which a reaction takes place. Okay, mathematically, for the steam reforming reaction coordinate is going to be the change in the mole of NC methane minus 1. So these are going to be stoichiometry coefficient in front of each species. So this is the reactant minus 1, reactant 2 minus 1, and then CO product, right? Delta NCO divided by 1, right? 1 is the stoichiometry coefficient, and then delta NH2 divided by 3. Okay, so these are the stoichiometry coefficients. Now for reactants, we know the change in the moles of the species is going to be negative because they are, you are consuming reactants to form products, right? So this is negative, but negative divided by negative, so it's going to be positive, right? And then your product is forming, right? So your delta NCO originally is going to be 0, right? You don't have any CO, but after reaction, if you form this product, then delta NCO is going to be positive, divided by 1 is going to be positive, right? Same thing for delta H2, right? It's going to be positive. Okay, so this reaction coordinate is really a positive value, right? By definition, okay? All right, so now we can actually come back to this generalized reaction, right? For a general chemical reaction, if you have V1, V2, all the way to V3, A3, V4, A4, right? And we already specify your stoichiometry coefficient is positive for products, negative for reactants. And then we go back to the reaction coordinate definition, right? So here, reaction coordinate is going to be delta Ni divided by Vi. So the change in the number of moles of species in I could be A1, A2, A3, A4, right? And then the stoichiometry of this particular species, right? V1, V2, V3, V4, right? So this is the definition. Now, what we can do is we can actually take differential on both sides, right? So d epsilon is just equal to going to be equal to d instead of delta, right? You have like d and I, right, divided by vi. So basically this is trying to understand at any instant time what is going to be your changing reaction coordinate depending on the instantaneous increase or decrease of a particular species in the system. Okay. All right, so this is your differential of the reaction coordinate. Now, if you integrate this reaction, right? If you integrate this equation, so basically, if you focus on Ni, right? Ni, let's say your initial moles is Ni0, right? If you don't have any products in the original reactor, then your Ni0 for those products is going to be 0. Okay. And then basically if you integrate, right, then you will get, right, you integrate here, you move Vi to the other side because these are stoichiometry coefficients. So basically they are constant values, right? Then basically you integrate on both sides. So it's going to be delta Ni is equal to Vi epsilon, right? And then Vi epsilon is equal to delta Ni, right? So you move Ni initial to the to this side. So Ni at any instant time or any reaction coordinate, your species, the mole of species I is going to be the initial moles plus Vi times epsilon, right? So now Vi times epsilon is basically the moles of species I that have been reacted, right? So if it's a reactant, right? Vi is negative, epsilon is positive, so you know your total moles of the I species inside the system is decreasing. But if you are talking about a product, right? Initial maybe 0, but epsilon is positive, Vi is positive. So with increasing reaction coordinate, your number of moles of species of your product is going to be increasing, right? So really this gives you a way to correlate how many moles of species are inside the system if you know the reaction coordinate or if you know the initial, and if you know the initial mole of the species at the starting point of this reaction. And then this Vi, you can, once you know the reaction, you can quickly find out your Vi values, okay? All right, so now this is integrating, right? But at any epsilon, so basically at any epsilon reaction coordinate, you know how to find Ni. And then you can also find out the total N, right? The total moles of all the product or all the species add together inside the reactor, right? So N is equal to summation Ni. And then it's basically, if you do that, right, it's going to be summation Ni0 plus epsilon summation Vi, right? Epsilon is universal across different products by definition, if you may, right? And then basically it's going to be epsilon times summation Vi. So basically you just like taking summation on both sides, and this is what you get, okay? And then summation Ni0 is basically the total initial moles of species inside the reactor, right? And then epsilon times summation Vi is basically the total moles of reactive species, right? And then usually we have like summation Vi to use just V to represent this summation, okay? Yeah, and then once you know the total moles and you also know the particular I and moles of the species I, you can actually calculate the molar fraction of species I at any reaction coordinate. So Yi, for example, the molar fraction is going to be, if it's a gas state reaction, then Yi is just equal to Ni divided by N, right? Total N. And then Ni, we already know Ni0 plus Vi epsilon. And then total N is going to be N0 plus V times epsilon, right? So we can also use N0 to represent the summation Ni0. So total initial moles plus the moles species reactive for I, and then divide by the total initial system moles, and then the total species reacted within the system. So now you can actually correlate your reaction coordinate with your molar fraction of the species at any instant time of the reaction. Okay. All right, so now the reason why we want to do all these is because we are trying to analyze reaction equilibrium, right? Once we have the reaction equilibrium, we can, calculate this epsilon, and you figure out the epsilon equilibrium, you figure out the equilibrium molar fraction. So that's basically the composition that we care about, right? So we care about if it's a reaction, right, at the end of the reaction, meaning that they reach equilibrium state, what is the how much product you will get, right? That will rely on the molar fraction, right? All right. So now for a chemical reaction to reach equilibrium, right? Basically, the Gibbs free energy of the system has to reach a minimum state. Okay. So now if you are so this is basically if you still remember dg, right? So dg is equal to I mean, actually you can actually read the additional slide in this lecture to better understand, right, why for a chemical reaction to reach equilibrium you have to minimize Gibbs free energy. Okay, but for now you just like know, right, as your reaction going on, this is the y-axis Gibbs free energy, and then x-axis is your reaction coordinate, right? So same system, let's say as the previous. So your Gibbs free energy initially will decrease, right? And then decrease to a minimum point, and then start to rise again. So this minimized Gibbs free energy state is actually your equilibrium state, okay? And at equilibrium, mathematically, usually again at constant temperature pressure, right, for this particular plot. Now, mathematically, what this converts to at equilibrium is basically summation VI, stoichiometry coefficient, mu I. Mu I is the chemical potential of each species, is going to be equal to 0. Again, in additional slide, you can I give you a derivation slide correlating these two. So if you are interested, you can see why at equilibrium this equation have to be true. Okay. Now we know what VI is, and then mu I we already taught you how to calculate mu I, right? So recall for the chemical potential of species I, the chemical mu I is just equal to GI0 plus RT natural log Fi hat divided by Fi0. Fi hat is the fugacity of species I in the mixture, right? And then here GI0 is just like the specific or molar Gibbs free energy for pure species I at the standard state, right? That's why we have 0 here. And then Fi0 is the fugacity of pure species I at the standard state, right? That's why we have 0 here. And then here, this one is basically the activity that we are talking about, like that we introduced in previous lecture, right? So activity alpha I hat is equal to just Fi hat divided by Fi0, right? So we already know how to calculate these, right? So in the end, right, your mu I chemical potential is just equal to GI0 plus RT natural log alpha I hat, right? So this is the standard state Gibbs free energy. Okay. All right. So now what you do is you plug this back into this equation, right? So you have this, and then you combine these two equations. What you will get is summation VI GI0, right? You are basically, plug this in as mu I, and then you split into like VI times GI0, VI times RT. RT is constant because constant temperature pressure. You move to the outside, and then natural log times VI, okay? And then mathematically, this summation is just going to be equal to natural log pi bracket AI alpha I hat to the power of VI. Now this pi is basically the product of all all the terms, right? So here pi is going to be alpha 1 V1 times alpha 2 V2 times alpha 3 V3, right? All sum up, all the way up, right? And then this is because, right, in order for you to understand the relation between this and this, you actually need to remember, right, natural log A1 plus natural log A2 is just equal to natural log the product of A1 and A2 and A3, right? So this is just like mathematical mathematical conversion. Okay. So now if you do that, right? So basically what you have is like pi. So basically you are replacing this with this, but now we are just like trying to rearrange the equation. So you move this to the other side. So you have like minus sign, and then you have IT. So you divide by RT on both sides. And then eventually you still have natural log in front, so you take exponential. So in the end, this whole thing is going to be just equal to exponential minus this guy divided by RT, okay? And then here, this whole thing, right? This is the standard state, Gibbs free energy of pure species, and the stoichiometry coefficient, right? Divided by RT, and this value you can look up. If it's a reaction, your VI is given, right? And then RT, once you specify temperature, you can actually calculate this whole thing, right? As a constant, right? At a particular temperature. And this constant, we give a name, it's called chemical reaction equilibrium constant. And we use K to represent this, okay? And then K only depends on temperature, as you will see, right? So for species GI0, you can find it because it's standard state pressure. So pressure is 1 bar already specified. BI, you quickly look up. So basically this K only depends on temperature, okay? And then if you define, right, this whole thing as K, you can actually take natural log of K and then take a minus sign, and then you quickly realize minus RT times natural log K is just equal to this whole thing, okay? Summation VI GI0, okay? And then from this definition, right, quickly you can write out your reaction equilibrium constant is equal to just like pi a alpha I hat to the I power, right? So this is the equation, just directly rewriting this equation to this equation. Now, also importantly from this here, this whole thing, summation VIGI0 is just equal to delta G0, right? Delta G0 is actually the standard Gibbs free energy of Gibbs energy of reaction at T and standard pressure. Now this delta G0, you can calculate from the delta GF, right? The standard Gibbs energy of formation at a particular temperature. So we will show you how to find those, and then you calculate this delta G0. Okay. And then if you replace this with delta G0, then you quickly realize, right, natural log K is going to be minus delta G divided by RT. And then you take exponential, right? So K is just going to be exponential minus delta G divided by RT. So these are just different ways of rewriting this equation. But these three equations are very important when you describe a chemical reaction equilibrium, okay? All right, so now let's talk about this delta G0, right? So this delta G0 is 0 means standard, right? So we are talking about standard Gibbs energy of reaction. And then if we specify the temperature is 298 K, then you have delta G0, 298. Again, standard state means the pressure is standard, which is 1 bar or 1 ATM, okay? Now, the equation for calculating the standard Gibbs energy of reaction is similar to the to that for calculating standard heat of reaction. So similarly, delta G 2980 is just equal to summation VI delta GIF 298, right? So basically, it's going to be the standard Gibbs free energy of formation at 298K on the product side minus the reactant side, right? And then this delta GIF, again, if you are talking about formation reaction, then your previous, constituent elements and molecular gases, those enthalpy are zero, then basically you can just actually say, right? So, no, or Gibbs free and Gibbs energy is zero. Then you can say delta GF is basically just like GIF is just like basically the standard state Gibbs energy of species I at the particular. If you assign the pure species, pure elements is zero, or pure molecular gases is zero, those Gibbs energy. Okay. All right, so basically what I'm trying to say is that from this equation, what you only need to do is look up for each species, what is your delta GF, right? And then you find your stoichiometry coefficient, you plug in, you calculate the standard Gibbs energy of reaction for your particular reaction, okay? So now here, delta GIF values are provided in Appendix C. So previous table, we already see some of it, right? Now, for delta GIF at different temperatures, right? So here, for the previous table, we are looking at 298K. But for other temperatures, you can actually find them in the literature. For example, in this particular source, you can actually look the delta GF values for different species, but at a different temperature, okay? Now here, just like quickly recap, this is like 298K, for example, right? For different species, you have like different heat of Gibbs energy of formation, right? Here, again, pay attention to the state of your species, right? If it's a gas state, benzene, let's say, right? Then your Gibbs energy of formation is slightly higher than the liquid state. So you need to pay attention every time when you look these values up, right? You actually need to look whether it's gas state or liquid state, and then find the corresponding values, and then plug into the equation to calculate the final Gibbs energy of reaction. Okay. All right, so that's now you should know how to calculate the heat of reaction and then Gibbs energy of reaction, and then also correlating reaction coordinate with the molar fraction of the particular species. Now we want to understand, right? What is the effect of temperature, right? Changing temperature, how temperature change will affect the reaction equilibrium constant K, okay? So if you recall from previous lecture, so we know partial G divided by RT, partial T is equal to constant pressure is equal to minus H divided by RT squared, okay? Now, you can just replace this G with delta G. Delta G is the Gibbs energy of this particular reaction, right? So D delta G RT divided by DT is, if it's again constant temperature pressure processes, right? You can actually take full derivative, because delta G, like I mentioned, is constant, right? Divided by RT. It only depends, delta G0 only depends on temperature, right? And then RT only depends on temperature, so you can take the derivative, right, with dt. So it's going to be, again, if you replace this with delta G0, then here you will have like delta H0. So this is the standard heat of reaction. This is the standard Gibbs energy of the reaction. And then this whole thing highlighted in red is going to be minus natural log K. So D minus sign cancel. So D natural log K dt is just equal to delta H0 divided by RT squared. Okay. So here you can see again, K depends on temperature only because K refers to a standard state. Standard state is because we already specify the pressure being 1 bar or 1 atm. So you no longer have any pressure dependence for this standard state system. Okay. So now if you look at this equation, right? D natural log dt is equal to delta H0 RT squared, right? So here, if we want to understand the effect of temperature change on the reaction equilibrium constant, right? Then we really need to know the sign of this delta H0, right? So now if delta H0 is negative, meaning the reaction is exothermic, giving out heat to the surroundings, then you can see, right, this is like negative, RT squared is always going to be positive, and then d natural log dt is going to be a negative value, right? So that means when you increase the temperature, right, your natural log K is decreasing. And then you're basically meaning that your K is decreasing. So for this particular reaction, exothermic reaction, your reaction equilibrium constant will decrease with increasing temperature. But now if you have like a endothermic reaction, which is like delta H0, okay? If it's a delta H0 is positive, then you can see, right? Positive, positive, so positive here, then the natural log K divided by dt is going to be a positive value. When the T increase, you actually increase the reaction equilibrium. So for endothermic reaction, equilibrium constant increase with increasing temperature, right? So now this is actually governed by Le Chatelet principle, right? So we will talk about that in more detail in the futures in a few slides. Okay. All right, so now coming back, so now we understand the temperature effect on the reaction equilibrium constant. Now we want to understand, right? What's the relationship between your equilibrium constant and the equilibrium composition, right? First, we can understand the gas phase, for example, okay? Gas phase reaction. So coming back to this equation, right? This is equation is always true. You just like derive it from chemical potential for equilibrium, okay? And then here, right, again, pi alpha I VI is equal to K. K is the standard related to standard Gibbs energy of reaction. So K is only a function of T, okay? And then alpha I, we know it's the activity of the species in the mixture, right? So activity is going to be fugacity in the mixture divided by fugacity of I as standard state, right? So we already know this. Now, standard state, again, we are talking about if it's a gaseous species, we are talking about ideal gas. And then for liquid and solid, we are talking about pure liquid and solid, and then at standard pressure, which is 1 bar, and then the temperature may vary, right? You can specify a temperature what you want, okay? All right, now for gas phase reaction, so let's say all the species in either reactants or product, they are all gas, okay? Then if you are talking about a gas state, standard state for gas, make sure you are talking about ideal gas state, right? So Fi0 is just equal to P, right? And then it's going to be 1 bar, right? So we already know that for ideal gas, the fugacity is just equal to its pressure, right? And then the pressure is P0, which is 1 bar, okay? And then therefore, right, for the standard state, I mean, so basically, you know what is Fi0, right? So this is just P0, which is 1 bar, right? Then you plug in, and then you can actually quickly realize your activity is just equal to the fugacity of your species I in the mixture, right? And then this fugacity in the mixture, we already know how to calculate it, right? So this is the fugacity of your ideal gas If it's ideal gas, then it's going to be partial pressure fugacity, right? But now, since we are talking about a real gas, then you actually need to times a fugacity coefficient, right? And then again, if it's ideal, then this fugacity coefficient equals to 1 for ideal gas, right? And in this particular case, if we assume ideal gas state, so basically this Vi hat is equal to 1. Okay, so alpha I is just equal to YIP. YIP is again the partial pressure of species I in the mixture. Okay, so now if we assume ideal gas state, right? Remember this value goes to 1, and then you can plug this back into this equation, and then you can rearrange the equation. Eventually, what you will get is for gas phase reactions. And then again, if we assume these are ideal gas mixture at low pressure, which is 1 bar, and then or high temperature. Okay. So here, if you rearrange the equation, what you will get is in the end, this temperature pressure epsilon relationship. So pi yi to the vi is equal to p minus v times k. Okay. Now, molar fraction, right? Remember, we already know how to correlate your molar fraction with your reaction coordinate from previous slide. And then here, K is basically a function of temperature, like we talked about in the previous slide. And then the pressure is the system pressure. And then these minus V is the summation of VI minus sign, right? VI is stoichiometry coefficient, which you can look up when you have the specific reaction set, right? So in the end, right, this equation really on the bottom line, like from on the lining correlation is basically between temperature, reaction coordinate, and pressure, right? And Vi minus V is these are just like constants, okay? Now, when you think about equilibrium composition, right? If we are talking about the reaction, right, the more product we have, right, then the higher the yield, right? So essentially, remember the product side is on top, right? Vi is positive, and then Vi is negative on the reactant side. So basically, if you think about, right, you have like some product of your product, multiply product multiply altogether, divide by reactant multiply together. So the larger the value, this value, the higher the yield, right? Meaning that the reaction push towards the product side. Okay. And then usually when we talk about a specific chemical reaction, what we usually want is if it's forming a particular product, right? You want to increase the yield of that product as much as possible by controlling your temperature pressure, okay? To reach the ideal, to maximize the yield. All right. So now if our goal is to increase equilibrium yield, right? So that means we are going to try to increase the this particular value, okay? And then at constant pressure, right? Constant pressure, if we perform the reaction at constant pressure, okay? We already know constant pressure process, d natural log dt, d natural log k dt is equal to delta H0 RT squared, okay? So if it's constant pressure, then this whole thing doesn't depend on pressure that much, right? Because your pressure is already constant, right? So you're not changing here. The only way to change this whole thing is by changing your K value. So you actually need to increase your K value, okay? So now for endothermic reaction, right, like I mentioned, delta H is going to be positive. So this whole thing is going to be positive. So in the end, right, when your temperature increase, your equilibrium constant is going to increase. So when your equilibrium constant increase, right, remember this doesn't change. So this whole thing will increase. And then when this whole thing increases, basically you actually reach a higher yield, higher equilibrium yield, right? So for endothermic reaction, you want to run your reaction at a higher temperature to reach a higher equilibrium yield, and vice versa. And if you have an endothermic reaction, delta H0 is going to be negative, right? Then you have like to have decreased temperature in order to increase your equilibrium constant, okay? So for exothermic reaction, you want to run the reaction at a lower temperature in order to reach a higher yield, okay? All right, now let's say if you run the reaction at constant temperature, right? If it's a constant temperature process, then your K value is fixed, right? So your K is not changing. Now you just need to know, right, how you can change this term in order to maximize the this whole thing or maximize the yield. Okay. Now this actually depends on the sign of this mu. Remember, this V is summation of VI, right? So we actually have two different types of reaction. So one is volume reducing reaction. So V is smaller than zero or negative. So basically summation VI, summation of your stoichiometry coefficients is negative. So here, right, for example, if you have like this reaction and 1 mole of H2 react with 0.5 moles of oxygen, giving you 1 mole of H2O. And then the V is going to be 1 on the product side, minus 1/2 on the reactant side, 1 minus 1 on the reactant side. So it's going to be minus 1/2, right? So this summation VI is going to be negative, right? So this is a volume reducing reaction. So if V is negative, then minus V is actually positive, right? So you actually need to increase the pressure to increase the overall yield, right? So when your pressure increase, this whole thing increase, then your yield increase. And then for volume increasing reaction, so in this particular case, right, you have 2 moles of NH3 goes to 1 mole of nitrogen and 3 moles of hydrogen gas. And then your total summation VI of V is going to be 1 plus 3 minus 2 is equal to 2, which is positive, right? So for V to be positive, minus V is going to be negative, right? So in order in order to increase this, then you need to really decrease the pressure in this particular case, right? So now, as you can see, right, for different types of reactions, right, you can actually manipulate your temperature and pressure to maximize your equilibrium yield, right? And they change in opposite direction, actually. So this is actually governed by Le Chatelier's principles. So if a dynamic, the statement is that if a dynamic equilibrium is distributed by changing the conditions, right, the system will respond by adjusting itself to counteract the change and restore a new equilibrium, right? So I will let you to go back to digest this statement by looking at these different trends, okay? All right, so that's gas phase reaction. And now let's move on to liquid phase reaction. So for liquid phase reaction, again, these are still true, right? In general, at equilibrium, this equation holds. And then K is only a function of temperature, right? Again, this also holds, right? You in the end, you just need to find the activity of your species I in the mixture, which is equal to just the fugacity of I divided by fugacity at the steady state, alpha I activity, okay? Now for standard state, if you are talking about liquid, now we are talking about pure liquid at a given temperature, okay? Now for liquid phase reaction, the fugacity of the species I in liquid solution, Fi hat, is equal to activity coefficient gamma I times xi is the molar fraction of species I in the liquid solution times fugacity of the pure species I at the system pressure and temperature. So this equation we already gave you in the previous lecture, so we are not going into detail, but you already know how to calculate gamma I. You already know how to uh, find xi, right? And then alpha I is basically activity is just equal to, right, this divided by Fi0. So it's basically gamma I xi times Fi divided by Fi0. Okay, Fi0 is the fugacity of pure species I at 1 bar, same temperature. So here we have the standard state. Okay. All right, now gamma I, you know how to calculate. Xi is simple, right? Now it's just like how you can calculate Fi divided by Fi0 for pure species at equilibrium temperature and pressure. Okay, I'm going to skip the math, but in the end, your Fi divided by Fi0 is basically going to be this whole thing, okay? And then if you go back, right, so you plug this back into this equation, you will actually have like this whole thing, but containing a Vi in the expression, okay? So I'm like basically, if you are interested in how you get this, you can read the additional slide. But basically, that's the result, right? After calculating this, you plug back in here, and then once you have this alpha I, you plug back into this equation. What you get eventually is going to be this whole thing for liquid phase reactions. So basically, all the species involved in reactions are liquids. Okay. And then here, right, if you look at this whole expression, if your pressure is approximately equal to 1 bar or low pressure, this is going to be approximately just equal to 1, right? So this whole thing is equal to 1 at low pressure, okay? So except for very, very high pressure, this equation basically on top can be simplified to this whole thing times 1 essentially is equal to K, okay, at low pressure. And again, K is a function of temperature, right? Xi, gamma I, you know how to find and calculate. Vi, you can calculate that, right? Now for ideal solution, right, gamma I is just equal to 1. So you can further simplify if this liquid phase reaction is actually ideal solution model. You can actually just like, you know, get rid of this gamma I, and then in the end, you just have pi xi vi is equal to equilibrium constant, okay? So just like if you look at this equation, right, you don't have any pressure terms because K only depends on temperature. Xi is just molar fraction of like your mixture, doesn't have any pressure in this equation. And then Vi you can look up by their stoichiometry coefficients, right? So this is different from the gas phase reaction. Gas phase reaction, remember you have a P term in the final equation, right? Pressure actually plays a role in your gas phase reaction because these gases are compressible, right? You have like partial pressure. But for these liquids, right, they are not very compressible. So that's why usually the total pressure has negligible effects on the liquid phase reaction equilibrium. Okay, so that's why your pressure doesn't come into play in this equation. Okay. All right. So you can also do the same thing, right? For endothermic, right? You are trying to increase the whole thing, right? Then you can change your temperature to maximize your reaction equilibrium. All right. So that's all for today. So hopefully by today, you learn how to apply thermodynamics to chemical mixing processes and also chemical reactions. You know how to calculate heat of mixing, heat of reaction, and also Gibbs free energy and reaction equilibrium, right? And then how you can actually calculate the equilibrium composition and also maximize the yield by changing the temperature and pressure, okay? So that's all for all the thermodynamic module that we want to cover in this particular course. And wish you luck for the rest of the modules. Thank you.